Hello everyone, I have not made a video for a long time, so I thought maybe I should make you aware of some of the recent research I have been doing. So I'm currently working as a researcher in residence at National Manufacturing Institute of Scotland, and we are trying to solve industrial problems. And in this case, we are trying to understand and predict the microstructure dependent sporadic fracture in near beta titanium alloys. If we talk about near beta titanium alloys, then it is used in many different applications. We are currently focusing on titanium 5553. And if you're not familiar, these numbers are basically the composition of this alloy, and each number denotes the composition of the alloying element used, such as aluminium, molybdenum, chromium, etc. These are some of the applications for 5553 alloy, and it's being used by Boeing in bulkhead castings. It is used in many landing gear components, which you can see on the middle and on the right hand side of the slide as well. And you can see for 787 main landing gear, a number of components are made up of titanium 5553 alloy. The problem with this alloy is, although it has superior mechanical properties than normal traditional titanium alloys, however, it shows sporadic failure. So if you look at the slide and look at this figure here, then you can see, depending on the process route one has used to manufacture a component, it can show a very wide range of ductilities, which is the point at which your component will fail. Similarly, heat treatment can also have an impact on the ductility as well as ultimate tensile strength. And also heat treatment conditions can have strong impact on the fracture toughness of the material. So these are two different types of heat treatment processes used, and you can see for BASCA process, the fracture toughness is almost twice as much as the other heat treatment process. These are some of our own results at AFRC, which is part of National Manufacturing Institute of Scotland. And you can see, depending on the reduction during forging, it also shows very wide range of ductilities. And this all lies in the microstructure of this material, as you can see in the EBSD map here, because it's a dual phase alloy, so it has alpha grains which are inside the beta matrix, as you can see here. And we are trying to understand how this microstructure really causes all these different types of failure and what causes that ductility to go down in certain cases. So we are using experimental facilities and data from NMIS. We are using our in-house CPFEM, which is crystal plasticity-based models, to model these kind of behaviors and then predict and identify the risk zones. Obviously, this will be beneficial for high-value manufacturing caterpillar centers as well as the industry partners who are involved in these centers. So our approach is very simple. We take the EBSD map, we reconstruct the microstructure, and we reconstruct the representative volume elements for each individual case. So this is one of the examples where one alpha grain was inside the beta grain. And then we try to understand and focus on how microtextural regions, alpha and beta phase, and slip localization contribute to early failure. So these are some of the results, and these results show, for example, in this case, the total slip, and for different orientations, and also for two different types of loadings. And you can see the deformation modes are very different. In this case, we see some wide nucleation and growth, while in this case, we see shear localization for this kind of loading. So we found out that the failure is linked to critical combinations of grain disorientations, localized slip bands, and also void nucleation and near alpha beta interfaces, which is the interface here, shows a lot of damage accumulation. And this is a simple animation of that for one of the orientations. So impact and takeaway, we are moving from average based safety margins to a location specific risk prediction. So we find out which locations are critical in the microstructure, as you see here. This will enable us to have smarter inspections, more reliable lab predictions, and material informed design improvements. And most importantly, we are trying to turn sporadic failure into a solvable science. Future directions are, this work is still ongoing, and we are still investigating many different types of microstructure features. And beyond this project, we're going to develop an AI and inspection assisted failure prediction framework in titanium alloys. Professor Brad Boeing, Dr. Salah Rahimi, and Dr. Abel Thompson are the ones who are supporting this work at AFRC and National Manufacturing Institute of Scotland. And I would also like to thank all my collaborators and researchers who are helping in this work. So if you have any question, you can always comment below. If you are interested in doing similar sort of research, then again, you can get in touch with me, and we are happy to collaborate with you as well. Thank you very much for listening, and have a nice day.